Okay, good evening, everybody. It's nice to see familiar faces in the audience, even if behind masks. And to those of you who are joining us online, we actually have people watching this live tonight. Welcome, everybody, to the second Our Universe Revealed of the semester. For those of you who haven't met me, I'm Jonathan Crass. I'm the series coordinator. And tonight, I am joined by a veteran of Our Universe Revealed and physics at Notre Dame. Professor Grant Mathews has been at Notre Dame now since 1994.
Yes.
I won't tell you how old I was, but I was in single digits when you started here as a professor. But Grant is an expert in all things cosmology, big things in the universe, extreme things in the universe. And tonight he is going to talk to us about the endpoints of stars. What happens when stars and things come to the end of their lives? What are we left with? And what kind of environment does that create? So for those of you online, if you have questions, if you're on Zoom, feel free to put them in the Q&A and we'll come to them at the end. And if you're watching on YouTube, put them in the chat and I'll keep an eye on them as well. So let's give Grant a warm welcome.
Okay. Thanks. This talk, the emphasis here is on supernovae, but I'm actually talking more about this part of the title, which sort of got blurred into the later. Supernovae are very interesting, though. I mean, and we'll go through supernovae. What I want to talk about, by the way, is some very new research just in the last few months that two of my graduate students have completed. I'm looking to see if they're here. They're not. But okay. Anyway, the question is how we can use neutron stars, black holes, and supernovae as a means to probe properties of matter at very, very high density. And I'll get into what that means. But yeah. Department of Energy pays me to study properties of matter at very high density and temperature. So let's see what we can learn. Supernovae is the start of our discussion here. And they produce matter at extreme density and temperature. What you saw there was sort of an artist visualization, a pretty accurate one of how a massive star, say 10 to 20 times the mass of the sun, when it runs out of its thermonuclear fuel, it collapses very high density, and it leaves behind that little white dot there, which will be either a neutron star or a black hole. And in fact, which is a problem we're still trying to figure out, whether it forms a neutron star or a black hole. And we'll get into that as we go along. So the theme of what I'm talking about, this is the universe revealed. How is the universe revealing itself through the properties of matter at very high densities? Okay, let's go on with that. There are really three places in nature that we're studying where the matter at the most extreme conditions possible form. We just saw, yes, supernovae, and they can produce neutron stars and black holes. Something I'm even more excited about now are colliding neutron stars. Just a few years ago, we had great excitement. The first two neutron stars colliding were observed, and the ripples in space-time went through the Earth, and we saw those ripples recorded in a thing called the Laser Interferometer Gravity Observer, LIGO. But what we are looking at today is the mysterious phases of matter that occur after those two stars merge when they get to their endpoint, which is usually a black hole, but it might also be a hypermassive neutron star. I'll explain what that is. There is a third place in nature where the most dense states of nature occurs, but I'm not going to talk about that. I do have a graduate student working on that, Miguel Carrera, who happens to be at the Theory Institute in Santa Barbara this week. But it's possible in the Big Bang, dependent upon how it's expanding and how the matter is being formed, that you get clumps of matter that collapse to very high densities. But that's a subject for another talk. Today, we're going to talk about these two environments. Okay, so let's think about what do we mean by the highest density states of matter? I mean, we know what we talk about states of matter. You take water, you cool it down, it turns into ice. That's another phase. It's a phase transition. It's a new phase of matter. If you heat it up, it turns into steam. It's another phase of matter. Well, it turns out there are dozens of very bizarre states of matter, phase transitions, that happened in the early universe and can happen in these extreme astrophysical environments. Let's just take an example. The sun's sitting out there, not yet setting in the west. Its radius about 700,000 kilometers, about 1.4 million kilometers across. It's supporting itself by thermonuclear explosions in the interior, the equivalent of about 1 billion megaton nuclear bombs going off every second. That's how much is holding that sun up. But it turns out in a short while, actually a long while, the sun will lose that thermonuclear energy. It'll burn up its fuel. If the sun suddenly stopped burning its fuel, it would feel its own gravity and start to collapse down. It would slowly, actually over a period of about 100,000 years or so, it would, and this will, well, it'll happen a little differently, but for this example, it'll keep going down till something that's 1.4 million kilometers across goes down to something that's, say, 10,000 kilometers across, about the size of the Earth. So once it becomes about 1/100th of its present size, there are 1 million Earths that could fit in the sun. The sun weighs about 1 million times the Earth, a little less than that. The atoms could form into a giant crystal. It becomes like, this is an artist's rendition again. Literally, the atoms form a regular lattice. It becomes a kind of star that we call a white dwarf. Now, for the sun, that phase of matter, actually, we think we understand pretty well. There are a few little mysteries about it, but not much. And just to show you a real astronomy picture, late in the early morning tonight, and later in the season when the constellation Orion comes up, it's always followed by its dog, his dog, Canis Majoris. And the bright star in the eye of the dog is this star, Sirius. And some decades ago, people noticed this tiny little dot going around Sirius. That's a white dwarf star that's orbiting the star Sirius. Okay, so we know about that phase of matter. But what happens if it wasn't the sun, but a star, say 10 times the mass of the sun or more? When it's out of its fuel, it's going to keep going down. So instead of just a giant atom with a regular lattice of atoms and electrons like a crystal, it's going to collapse down until the electrons in that matter absorb into the protons, forms a bath of pure neutrons. This will be pure neutron matter. We call this a neutron star. And for example, this is a picture of the Crab Nebula. If you look at the center, there's a little dot there. That's a neutron star that's signaling us by its presence because it's emitting X-rays. But that's a star 10 or 20 times the mass of the sun that compressed down to about the size of South Bend. So it's like a single giant nucleus, but it's not a normal giant nucleus. It's a new phase of matter that we're trying to understand. There are hundreds of theories, mathematical models for what this matter looks like. We don't yet know which one is correct because it's a very complicated mathematical problem to solve. The motivation of the work my graduate students are doing is to say, well, as they form in a supernova, maybe we can see something that tells us which is the right of those hundreds of theories of what that matter looks like. Okay, but what would happen next? Even stars in that mass range and heavier stars don't always form a neutron star. It used to be, we thought, oh, everything from up to 20 times mass the sun forms a neutron star. Textbooks still say that, but in fact, in the last 5 to 10 years, we've realized some form a neutron star, some form a black hole. I'll show an illustration of them. But if they lose the support from the neutrons, they merge. Okay, there's a first step. If they get just a little bit tighter together, they form a new form of matter. And that's a major thing we're looking at, quark matters. Inside every neutron, every proton and neutron are 3 more fundamental particles. They're called quarks. And once the matter gets squeezed together, the neutrons dissolve and you have pure quark matter. It's very mysterious. We don't really know the properties. We have a theory, but it's very difficult to compute. And there are many complicated phases that are theories of what happens in quark matter. This is a very technical slide, so I'm sorry about it. But this shows temperature, and this is, it says mu there, but think of that as density increasing. Normal nuclear matter, neutrons, protons, would be low temperature and low density. But as we heat up to many times normal density of nuclei, we form these different phases. They're called color locked, KN condensate, superconducting, color, flavor. They have all sorts of names. There's a whole zoo of things, but we can't really see those except they're formed as a star that's a neutron star gets a little heavier, maybe by merging with another neutron star, or a very big supernova starts going down into quark matter. This, for example, is a picture of one of what our simulations would take you through these phases of matter, of how the temperature and density changes as one of these collapses occur. Okay, so this is what we're trying to understand, but wait, there's more. What happens next? If it starts going down to the size, take some of the size of the sun, convert it to the size of campus, about 1 kilometer or 2, 3 kilometers in diameter, you'll form a black hole. I could spend a whole hour talking about the intricacies of black hole, how time stops as you get to the edge of a black hole. In fact, if you're falling into a black hole, you'd look up and you'd see the entire infinity of time go past before you ever crossed it, because your time slows down almost to 0 compared to the rest of the universe. But that's not what we're talking about today. We're talking about how the star collapses, the black hole forms. There are other states of matter that arise. There's something called electroweak symmetric matter, grand unified matter, maybe supersymmetric matter. Ultimately, it's going to collapse down to, this is a picture from one of Kip Thorne's books, of a kind of a space-time quantum foam, or a little point of superstrings with the size of about 10 to the minus 33 centimeters. We're trying to study that too. But mainly what I want to talk about today is the formation of the neutron-like matter and the formation of the quark matter. Those are the things we have a chance to look at. These things probably happen inside the horizon of the black hole, which means we can't ever see them. Okay, so the basis of this UND supported research is, as one of these things forms, matter's compressed to very high density, and we're trying to see what we can learn about those mysterious new phases of matter. First, I want to talk about, this is my graduate student, Luca Baccioli, who I thought would be here. But yeah, okay, we're all busy. He has developed models to describe a supernova. I'll show a little computer simulation in a minute. The way in which a star explodes is actually very poorly known. But after decades, more than 5 or 6 decades of computer models, we're finally getting a picture of how they explode. We're using that to try to explore how, as those stars form these exotic phases of matter, how it affects the explosion, because then we have a chance to see it. So we're looking at a thing called the nuclear equation of state, but that's just saying it's one of those exotic phases of matter. That's the technical term for it. This is a movie. Actually, I want to stop that. So let's hold on for a second. Let me go back to the start. Okay, I'm gonna do it this way. Okay, now I want to stop it there. Okay, what you would have seen as the movie started is the materials flowing in, the stars collapsing. This is on a scale of 1,000 kilometers. This inner 10 kilometers is that neutronized matter that's starting to form. Those electrons are getting absorbed into the protons. What you're seeing here are two a little bit technical things. This is the entropy in the star. What's entropy? I mean, you learn in the sort of freshman chemistry, you take a deck of cards, you throw it in the air, it turns random. That's the tendency of nature to make everything random. More technically, it's the amount of heat per degree that's getting shoved into a material. But what this is showing is that as the star collapses, there's an entropy that begins to form inside that newly formed neutronized matter. That entropy turns out to be a secret for deciding which star is going to explode and which doesn't. But the entropy is very dependent upon those hundreds of models of how we describe that matter. Now, this line here is actually showing 3 things. So I'm going to advance just a little bit so you can see what's going on. Okay, let's stop there. Okay, the inner line is that the edge of the neutronized matter that's forming. This outer line is material that's being heated by radioactive neutrinos that are being emitted as this material is getting converted into the neutron matter. That heated material pushes out this outer line, which is basically a shock wave plowing out through the rest of the star as the rest of the star is trying to come in. What's shown on this side is, as that's going on, that heating, that entropy generates a turbulence in the matter. And it's actually that turbulence that's going to drive the explosion. The key that we're unraveling here is that the properties of this neutron star generates the heating in this region, which generates the turbulence out here that causes the star to explode. Let me just finish the movie so you get the picture. Oops. There it is. We'll just run it from the beginning. Matter's falling in. It starts to form the neutron star. The entropy is generated out here. There's this turbulent heating that's being caused by those neutrino particles coming out. That's the edge of the neutron star compressing to higher density. And then this shock wave goes out as the star explodes. Now, we've studied dozens of those different versions of how the properties of the neutron star form. For different mass stars, when they go to explode, there's a 9 solar mass, 15, 20, 25. Now, what you're seeing is that outer shock radius trying to get out. If the star doesn't make it, decides to be a black hole, this explosion that gets started collapses back down, and this radius here is going to collapse down in time to a black hole. So these stars form black holes, these explode, these different colors in this bunch of zip codes here correspond to different theories for what that matter looks like. So what we're determining is that the very fact that stars explode at all tells us certain things about the way, certain things about some of this matter can explode and some can't. That matter that forms this properties of that neutronized matter. And there's more to it. I think I have another slide here. The amount of energy that comes out, which is what we ultimately see. This is a measure of the energy that's coming out of the star. And some of those theories give a lot of energy, some give a little. So by measuring supernovae, seeing how much energy comes out, we're determining what are those properties of that neutronized matter as it forms. Okay, the next thing I want to mention in the last 10 minutes or so is the other topic that I'm even more excited about than what we're learning about how neutron stars explode and what they are telling us about those properties of neutronized matter is what happens as you form a black hole. This is a simulation one of my students did with one of those same theories of the neutronized matter. 2 neutron stars come in, complicated theory of relativity things going on here, but that little dot formed in the middle, let me run it again just for fun. There's a little dot formed in the middle, that's gonna be the black hole that's gonna sink down and vanish right there. Bye. Okay, so there's a lot of information in that, and we're greatly aided by the generation of gravitational wave observatories because now all of that detail of the flow of matter gets imprinted on the gravity waves that come out. Now, let me say, what can we discover as this happens, as that matter flows to a black hole? This, for example, is a paper that my graduate student, Atul Kadia, who's just finishing his thesis. In fact, he's starting his next job almost already. This is just an illustration. There's a lot of technical detail. Remember that complicated diagram of all those phases of quark matter that I showed early on? This is an example of a very strong version of those phases. And this is an example of those phases kind of just slightly happen. Now, both of these are the exact same stars, the exact same mass. The only thing different is when they form the quark matter, it's going to be slightly different in this one. And the difference is actually quite dramatic. These stars, because the quark matter has more pressure, even in their interior, is delaying the time for collapse. This one is already gone at about 4,000 in this time unit, 1,000 of these, like 5,000th of a second. So it happens fast, but this one's gonna keep going and going and going and going. The quark matter is causing a pressure that prevents these stars from collapsing. And in fact, this never vanishes away. It actually keeps on as a hyperneutron star. It doesn't, with quark matter interior, it never actually goes down to a black hole. Now, the way we will see that in nature, this is an example of what we call gravity waves. As two stars go around each other, this measure going up and down is literally the Earth will expand and contract as that gravity wave goes through. Time will slow down as a wave goes through, while space is expanding and contracting as that wave goes through. They all start out exactly the same. If you have just normal matter, they get together a little bit, then they wind around each other, then they collapse and it's gone. But if you form this strongly interacting quark matter, which is what I'm very excited about, this goes on for a long, long time. And this is what the next generation of gravity wave detectors can see. We've calculated the signal and sure, they'll see that. So what we're excited about is that this kind of exotic quark matter, we can actually determine the properties of it by looking at what's called the ring down, this extended high frequency, it's like 3,000 cycles a second, gravity wave as it impinges on Earth. So that's really sort of the quick 30-minute overview of what I wanted to tell you. Let me just summarize the conclusions again. Supernovae can be used, we're finding best, to explore what's going on with that neutron matter, that newly formed neutron star, as that massive star, the core of it collapses and explodes. And we're still going through details of that, but we can see a very strong sensitivity to the different theories. The second thing is these gravity waves from neutron stars as they merge have the possibility to tell us a lot about the properties of this exotic quark matter as it forms. And with that, I'll stop and take questions.